Alright, welcome to the class. So from today on, we're going to have a look at the fourth chapter, which is chemical bonding. And today, we're going to have a look at the first topic, 4.1, types of chemical bonds. With a few rare exceptions, everything that you see, taste, or touch is made up of atoms or ions of elements connected to other atoms or ions by chemical bonds. Chemical bonds hold the world as we know it together. What exactly is a chemical bond? In earlier science courses, we learned that a chemical bond is an electrical attraction that holds atoms or ions together in a molecular element or in an ionic or molecular compound, which is shown here in figure 1. When bonds form, the atoms or ions that are joined function as a unit. Atoms combine to form molecular elements or compounds. Molecular elements are molecules that consist of atoms of the same element, such as nitrogen gas, which is denoted by N2. Molecular compounds comprise items of two or more different elements. Finally, an ionic compound is a pure substance composed of two or more ions combined in a fixed ratio. Okay, next, let's have a look at ionic compounds and ionic bonding first. When solid sodium, which is denoted by Na, and chlorine gas, or Cl2, react to form solid sodium chloride, or NaCl. A transfer of electrons occurs from the sodium atoms to the chlorine atoms to form sodium ions, or Na+, and chloride ions, or Cl-. The electron transfer occurs because chlorine atoms have a much higher electronegativity than sodium atoms, and hence have a very strong attraction for the sodium atom's single valence electron. The sodium and chloride ions now have opposite electric charges. As we know, oppositely charged objects attract each other. An ionic bond is a chemical bond between oppositely charged ions. Ionic compounds form when an atom that loses electrons relatively easily reacts with an atom that gains electrons relatively easily. Typically, an ionic compound results when a metal element reacts with a non-metal element to form positively charged and negatively charged ions that are held together by electrostatic attraction. The electrostatic attraction between positively charged sodium ions and negatively charged chloride ions creates a crystal lattice of sodium chloride, NaCl, which is shown here in figure 2. The chemical formula for sodium chloride is the example of a formula unit. It represents the smallest quantity of sodium chloride that has this chemical formula. The formula unit of sodium chloride indicates that the sodium and chloride ions combine in a 1:1 ratio. Note that crystal formation only occurs when a large number of positive and negative ions come together. This configuration is more stable than if the ions were separated into individual formula units. The ions in the crystal lattice are arranged so that the attractions between opposite charges are maximized and repulsions between like charges are minimized. This concept is shown here in figure 2b. To illustrate behavior of electrons in ionic compounds, consider the ionic compounds that form from elemental calcium, or Ca, and oxygen, O2. You can predict the compound that will form by examining the valence electron configurations of both calcium and oxygen. So the electron configuration for calcium is AR followed by 4s2. And the electron configuration of oxygen element is helium followed by 2s2, 2p4. Recall that the electron configurations of the noble gases are generally the most stable, right? Atoms and ions are more stable if they have the same number of electrons as the noble gas closest to them in the periodic table. That is, if they are isoelectronic with a noble gas. So, calcium would be more stable if it lost some electrons to become isoelectronic with argon, which has electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Similarly, oxygen would be more stable if it gains some electrons to become isoelectronic with neon, which has electric configuration 1s2, 2s2, 2p6. If calcium transfers 2 of its electrons to oxygen, both items can achieve a noble gas configuration for the electrons in their valence shells. The new electron configuration for oxygen now becomes the same as that of a neon, because its valence orbital now has 8 electrons. By losing 2 electrons, calcium achieves the electron configuration of argon. This configuration results in the calcium also having 8 electrons in its valence orbital. And this concept is illustrated in the formula on the top right. To predict the formula of the ionic compound, remember that chemical compounds are always electrically neutral, right? So the number of positive charges balances the number of negative charges. In this case, both the calcium ions and the oxygen ions have equal but opposite charges. Therefore, the formula unit for calcium oxide is CaO. Alright, next let's have a look at molecular elements and compounds and covalent bonding. This is another type of bonding we're going to have a look at in this lesson. When a metal and a non-metal react to form oppositely charged ions, an ionic bond develops. What kind of bond develops between two items that are similar or even identical? Consider what happens when two hydrogen atoms move close together. Remember that a hydrogen atom has one proton and one electron, right? The attraction of each electron by the proton of each hydrogen atom creates a force that pulls both atoms towards each other. When the hydrogen atoms are a certain optimum distance from each other, the attractive proton-electron force balances the repulsive proton-proton and electron-electron forces. The resulting hydrogen molecule is more stable and therefore has lower energy than the individual atoms that comprise it. This concept is illustrated here in Figure 3. So the type of bond that forms when atoms share electrons is called covalent bond. These shared electrons are called bonding electron pairs. Covalent bonds typically form between atoms of non-metal elements. Are you clear? So in a summary, covalent bond is a chemical bond in which atoms share the bonding electrons, and bonding electron pair means an electron pair that is involved in bonding, found in the space between two atoms. Okay, next let's have a look at Lewis' theorem of bonding. In 1916, Gilbert Lewis provided the first straightforward view of chemical bonding. He gathered information about chemical formulas, valence electrons, and models of the atom in an attempt to understand chemical bonding. From the data he collected, Lewis made predictions about the nature of bonding in what is now known as the Lewis theory of bonding. Ideas from his theory include the following main points. First, atoms and ions are stable if they have full valence shell of electrons. Second, electrons are most stable when they are paired. Third, atoms form chemical bonds to achieve a full valence shell of electrons. Fourth, a full valence shell of electrons may be achieved by an exchange of electrons between metal and non-metal atoms. Fifth, a full valence shell of electrons may be achieved by the sharing of electrons between non-metal atoms. And last, the sharing of electrons results in a covalent bond. So, based on this theory, Lewis drew structures to represent pure substances. A Lewis structure shows the arrangement of electrons and bonds in a molecule or polyatomic ion. After making observations of thousands of pure substances, chemists have identified rules for drawing Lewis structures. As we have already learned, the most important requirement for the formation of stable substances is that the participating atoms are isoelectronic with noble gases. Hydrogen, in the first period of the periodic table, followed the Duet rule, which states that a hydrogen atom forms stable configurations when it shares two electrons, represented by dots, to obtain a full valence shell. So this concept is shown here in figure 5. So as you can see here in figure 5, when two hydrogen atoms combine, they can form the hydrogen molecule, and they share a pair of electrons. So in this manner, hydrogen atoms become isoelectronic with helium atoms, which is shown here in figure 6. A helium atom has two valence electrons, so its valence shell is already full, which has configuration 1s2, right? Consequently, helium does not form bonds. So, as you can see here, figure 6 shows the Lewis symbol of a helium atom. A Lewis symbol shows the valence electrons in an atom of each element. Lewis symbols of atoms are used to draw Lewis structures of pure substances. Atoms of nonmetals in period 2 of periodic table, or carbon through fluorine, form stable configurations when they obey the octet rule. The octet rule states that many atoms form the most stable substances when they are isoelectronic with neon. Neon is a noble gas, which does not form bonds because each neon atom already has an octet of valence electrons, right? This concept is shown here in figure 7, which is a Lewis symbol of a neon atom. Yeah, in atoms of a period 2 nonmetals, the valence shells consist of single 2s and 3 2p orbitals. Each orbital can hold at most 2 electrons, right? So 8 electrons fill the valence shell. For example, the fluorine F2 molecule has a total of 8 valence electrons surrounding each atom, which is shown here in figure 8. Each fluorine atom is now isoelectronic with neon. Are you clear now? So even though each fluorine atom shares one of its electrons with the other fluorine atom in F2 molecule, it also has 3 pairs of electrons that are not involved in bonding. Pairs of electrons that do not participate in chemical bonds are called lone electron pairs. So usually we can follow these steps to draw Lewis structure. Okay, let's summarize the main steps for drawing the Lewis structure. So first, we need to identify the central item, which is usually the element with the highest bonding capacity. Write the symbol for the central item, then arrange symbols of the item for the rest of the elements in the pure substance around it. Second, add up the number of valence electrons available in an item of each of the elements. This number represents the total number of electrons or dots we will draw in our Lewis structure. If the structure is polyatomic ion, add 1 electron for each unit of negative charge, or subtract 1 for each unit of positive charge. Third, place 1 pair of electrons between each adjacent pair of items. Every 2 of these dots represent a bounding electron pair that forms a single covalent bond. Fourth, place pairs of remaining valence electrons as lone pairs on the surrounding items. Follow the dual rule for hydrogen items and the octet rule for all the other items. Fifth, determine how many electrons are still available by subtracting the number of electrons you have used so far from the total number of valence electrons. Sixth, place the remaining electrons on the central item in pairs. 7. If the central item does not have a full octet, move lone pairs from the surrounding items into a bounding position between those items and the central item until all octets are complete. And last, if the surrounding items have complete octets and there are electrons remaining, add these electrons as lone pairs onto the central item or items. Check the finished structure. All items except hydrogen should have a complete octet, counting shared and lone pairs to complete the Lewis structure. If you are representing a polyatomic ion, place square brackets around the entire structure and write the charge outside the brackets. So basically we can follow the 8 steps to write the structural formula of a molecule or polyatomic ion. And based on that, we can remove the dots representing the lone electron pairs and replace the dots representing bounding electron pairs with solid lines to represent covalent bonds. And use double or triple lines for double or triple bonds. Are you clear? Okay, if you don't have any questions, next let's have a look at a tutorial and a sample problem drawing Lewis structure. So in this tutorial, we will practice drawing Lewis structures for various of substances containing elements from the first 2 periods of the periodic table. We will also write structure formulas for substances based on their Lewis structures. So consider sample problem 1 here. Methanol or formaldehyde is a gas with distinct odor. Formaldehyde is used in the production of cosmetics, pharmaceuticals, and textiles. The chemical formula of this molecule is H2CO. Can you draw the Lewis structure and then write the structural formula of this molecule? Okay, I'll give you some time to consider this question by yourself, and then we'll have a look at the solution together. Okay, you can start now. Alright, let's have a look at solution together. So step 1, identify the essential item, which is the element with the highest bonding capacity. Write the symbol for a certain item and arrange the symbols of the items for the rest of elements in the substance around it. So in the molecule of H2CO, we know the essential item of methanol is carbon. And then step 2, add up the number of valence electrons available in an item of each of the elements. This number represents the total number of electrons, or dots, we will draw in our Lewis structure. Since methanol is not a polyatomic ion, we do not need to make changes to this number to compensate for charges. So one carbon atom contains 4 electrons, 2 hydrogen atoms have 2 electrons, 1 oxygen atoms have 6 electrons. So in total we have 12 electrons, right? Then step 3, we can place 1 pair of electrons between each adjacent pair of atoms to represent the bonding electron pairs. Record the total number of electrons available and the number of electrons used so far. So we have used 1, 2, 3, 4, 5, 6, and then we have remaining 6 electrons, right? Then step 4, place pairs of remaining valence electrons as lone pairs on the surrounding items, not the central item. Follow the Diode rule for any hydrogen items and the octet rule for all other items. Then in step 5, we can determine how many electrons are still available by subtracting the number of electrons we have used so far from the total number of valence electrons. So until this step, we have used all of the 12 electrons, so there are remaining 0 remaining electrons, right? Because there are no remaining electrons in this case, we can skip step 6. Otherwise, you need to place the remaining electrons on the central items in pairs. And in step 7, if the central items or item does not have a full octet, we can move lone pairs from the surrounding items into a bounding position between these items and central item until all octets are complete. Okay, step 8. If the surrounding items have complete octets and there are electrons remaining, we can add these electrons as lone pairs onto the central items. Then check the finished structure. All items except hydrogen should have a complete octet, counting shared and lone pairs. This is not a polyatomic ion, so no square brackets are needed. And then our Lewis structure is complete. In the last step, to draw the structural formula, we can remove the dots representing the lone pairs. Then replace the dots representing bonding electron pairs with solid lines to represent covalent bonds. Then use double or triple lines for double or triple bonds. And methanol is a neutral molecule. We do not need to represent a charge. So the structural formula for methanol is complete as it shows here. Any questions? No? Alright, so following the same method, next let's have a look at the Lewis structure for a polyatomic ion. So consider sample problem here. Sodium nitrate, NaNO3, is a versatile compound used in many products such as fireworks, pottery, enamel, and even as preservative in smoked meat. It contains the polyatomic ion called nitrate. NO3 with 1 negative charge. Can you draw the Lewis structure and the structural formula for nitrate? NO3 with a one negative charge. Again, I'll give you some time to consider this problem by yourself, and then we'll have a look at the solution together, okay? Okay, let's have a look at the solution together. Step 1, again, identify the central item and write its symbol. Then arrange symbols of the items for the rest of the elements around it. So in this case, nitrogen is a central item. And step 2, add up the number of valence electrons available in each of the items. This number represents the total number of electrons or dots we will draw in our Lewis structure. If the structure is a polyatomic ion, add 1 electron for each unit of negative charge, or subtract 1 for each unit of positive charge. So we have a -1 charge here, right? So we need to compensate this by adding 1 electrons. And the total number of electrons is 24 in this case, right? Then in step 3, place 1 pair of electrons between each adjacent pair of items to represent the bonding electrons. So at the beginning we have 24 electrons, and after this step we have used 6 electrons. In step 4, then we place pairs of the remaining valence electrons or lone pairs on the surrounding items, following the dual rule or octet rule appropriately. And now in next step, step 5, determine how many electrons are still available. So at the beginning we have 24, and after this step we have used all of the 24 electrons, so there are none left. Then we can skip step 6. We don't need to place any electrons on the central items because all of them are used. And then in step 7, the central N item has a incomplete octet, so we need to move a lone pair on 1 oxygen item to between oxygen and nitrogen items. And in step 8, there are no electrons remaining. Since we are representing a polyatomic ion, then we need to place brackets around the entire structure and write the charge outside the brackets. The Lewis structure is now complete, which is shown here in the figure after step 8. And to get its structure formula, we need to remove the dots representing lone electron pairs and replace the dots representing bonding electron pairs with solid lines. Then the figure on the bottom is the structure formula for the nitrate ion. Did you get it? Okay, next let's have a look at the exceptions to the octet rule. When drawing Lewis structures for molecules, hydrogen items always obey the dual rule, and carbon, nitrogen, oxygen, and fluorine items and other halogens obey the octet rule in all circumstances. However, there are exceptions to the octet rule. The first exception applies to molecules with central items that are surrounded by fewer than 8 electrons. These central items are said to have underfilled octets. The second exception applies to molecules with central items that is surrounded by more than 8 electrons. These central atoms are said to have overfilled octets. Boron, for example, forms compounds in which a boron atom has fewer than 8 electrons around it. The boron atom therefore has an underfilled octet. Boron trifluoride, or BF3, is a gas at normal temperatures and pressures, which is shown here. The Lewis structure for boron trifluoride is shown here in figure 12. It reacts very energetically with molecules such as water and ammonia, which have lone pairs of electrons that do not participate in chemical bond. The boron atom has 3 valence electrons, and each fluorine atom has 7 valence electrons. Therefore, boron trifluoride has a total of 24 valence electrons. In this structure, each fluorine atom has 3 lone pairs of electrons, which total to 18 electrons. The remaining 6 electrons surround the boron atom, causing it to be electron deficient. The reactivity of boron trifluoride with electron-rich molecules such as water and ammonia occurs because the boron atom is electron deficient. The molecule that forms from the reaction of boron trifluoride with ammonia has the chemical formula H3NBF3. Figure 13 shows the reactants and products of this reaction using simplified Lewis structure. In the simplified Lewis structure, dots representing bounding electron pairs are replaced by solid lines, and any dots representing lone electron pairs are kept. So, in this molecule, as shown here in figure 13, the boron atom obtains an octet of electrons. Some items can exceed the octet rule or have an overfilled octet, as we said before. These items use nearby vacant d orbitals to exceed their octet. Therefore, you do not observe this behavior for elements in periods 1 or 2 of the periodic table. An example of an item exceeding the octet rule is a sulfur item in sulfur hexafluoride, or SF6. A space-filling model shows the relative sizes of the items and their relative orientations in 3-dimensional space. So here, figure 14 shows a space-filling model of sulfur hexafluoride. Sulfur hexafluoride is a very stable molecule. The sum of the valence electrons in this unusual molecule is as follows. So one sulfur atom has 6 electrons, 6 valence electrons, 6 electrons, and 6 fluorine atoms has a total of 42 electrons. So we have total valence electrons equals 48, right? And figure 14 shows the arrangement of electrons around the sulfur atom and in sulfur hexafluoride. And note that in figure 14 that 12 electrons form the SF bonds. The total number of valence electrons is 48. So there are 36 electrons unaccounted for. Since fluorine atoms always follow the octet rule, we can complete the octet for each of the 6 fluorine atoms to give the Lewis structure shown here in figure 16. So this structure uses all 48 valence electrons for sulfur hexafluoride, but the sulfur atom has 12 electrons around it, which exceeds the octet rule. So how this is possible? To answer this question, consider the types of valence orbitals that are available for second and third period elements. The second period elements have 2s and 2p valence orbitals, right? The third period elements have 3s, 3p, and 3d orbitals. As we examine the electron distribution of the atoms in the third period, notice that as we move across the periodic table from sodium to argon, the 3s and 3 orbitals fill with electrons, but the 3d orbitals remain empty. The valence orbital diagram for a sulfur atom is as follows. The sulfur atom in a sulfur hexafluoride molecule can have 12 electrons in its valence shell by using the 3s, 3p together with the 3d orbitals, right? Do not forget there is a 3 orbital in the third period of elements. Okay, so following these rules, let's have a look at another practice of drawing simplified Lewis structures of molecules that are exceptions to the octet rule. So consider the sample problem 1 here. Molecules with underfilled octets. Beryllium forms compounds in which the beryllium atom has fewer than 8 electrons around it. Can you draw the simplified Lewis structure for a molecule of beryllium chloride, or BeCl2? Again, I'll give you some time to consider this question by yourself, and after that we'll have a look at the solution together. Okay? Alright, let's have a look at the solution together. Step 1, identify the essential item and write its symbols, and arrange the symbols of the items for the rest of the elements in the molecule around it. And then step 2, count all the valence electrons for all the items in the molecule. Total represents the total number of electrons, or dots, we will draw in our Lewis structure. So in this step, we have identified there are total 16 electrons. And step 3, we can place one pair of electrons between each adjacent pair of items, forming single valence bonds. And in step 4, we can place pairs of the remaining valence electrons as lone pairs on the surrounding items, following the duet rule or octet rule as appropriate. And then in step 5, we can determine the number of electrons still available. Apparently, there are none available electrons after we have conducted step 4. Then in step 6, we can skip step 6 because there are no remaining electrons, right? And in the next step, the central beryllium atom has an incomplete octet. We could move one lone pair of electrons from each chlorine atom to complete the octet for the beryllium atom. However, since we know that the beryllium atom will be underfilled when it forms a compound, the Lewis structure of beryllium is best represented as follows. You do not need to move the lone pairs of electrons from chlorine atom to beryllium atom. And in step 8, there are no electrons remaining, so the Lewis structure for beryllium chloride is complete. Then in the last step, if we replace the dots between items with lines to represent bonds, then we have obtained the simplified Lewis structure. Are you clear? Be careful with the exceptions. There are a lot of exceptions in chemistry. Okay, if no problems, let's have a look at another sample problem. Phosphorus forms molecular compounds in which the phosphorus atom shares more than 8 electrons. Can you draw the simplified Lewis structure for molecule phosphorus pentachloride, or PCl5? Alright, let's have a look at solution together. So again, in the first step, we identify the central item and write the symbol. Then arrange the symbols of the items for the rest of the elements in the molecule around it. The central item in this case is the phosphorus atom. In step 2, we count all the valence electrons for all the items in the molecule. The total represents the total number of electrons to draw in our Lewis structure. So that there are 40 electrons in total. And in the next step, we place one pair of electrons between each adjacent pair of items, forming single valent bonds. Draw one pair of electrons between each chlorine item and phosphorus item. We will have a total of 10 electrons around the phosphorus atom. Since we know that the phosphorus atom is overfilled, then we can accept this arrangement, right? Then in step 4, place pairs of the remaining valence electrons as lone pairs on the surrounding items, following the dual rule or the octet rule as appropriate. And apparently, if you do this in the next step, we can find the number of electrons still available is 0. So we can just skip step 6 because there are no remaining electrons. And each chlorine item has a full octet, and the phosphorus item is overfilled, so we don't need to move any electrons. In step 8, there are no electrons remaining, so the Lewis structure for phosphorus pentachloride is complete. Then to get its simplified Lewis structure, we can just replace the dots between the items with lines. So the figure on the bottom right shows the simplified Lewis structure for phosphorus pentachloride. Do you get it? Okay, if you don't have any questions, let's have a look at the last concept in this lesson, which is coordinate covalent bonding, which is a covalent bond in which the electrons involved in bonding are formed from one atom. So when two hydrogen atoms form a covalent bond, each hydrogen atom donates one electron to form the bond, right? We have already known this. However, sometimes a covalent bond that forms between two items involves two electrons donated by a single atom. This type of bond is called a coordinate covalent bond. One example of this type of bond occurs in the ammonium ion, or NH4 positive 1. In this ion, the nitrogen atom contributes 5 electrons, and the 3 hydrogen atoms each contribute 1 electron to the structure. A single covalent bond forms between the nitrogen atom and each of the 3 hydrogen atoms to form a molecule of ammonia, or NH3. Plus, 2 valence electrons of the nitrogen atom do not participate in bond formation. When a hydrogen ion, or H+, interacts with a molecule of ammonia, it forms a covalent bond with its remaining electron pair. This concept is shown here in figure 17. Both of the electrons that make up this covalent bond come from the nitrogen atom. Another example is aluminum chloride. Aluminum chloride can exist in 2 forms, given by the formulas AlCl3 or Al2Cl6. The molecule Al2Cl6 has a coordinate covalent bond. A molecule of Al2Cl6 forms from two molecules of AlCl3. A loose structure of AlCl3 reveals that the aluminum atom does not have an octet of valence electrons. Both sets of electrons involved in the coordinate covalent bonds come from the chlorine atoms. This concept is shown here in figure 18. These are, as shown here in figure 17 and figure 18, these are the examples of coordinate covalent bonding. I hope you can understand that now. Okay, so this is pretty much about today's lesson. And please find today's homework and reading materials in Google Classroom, and remember to complete your homework and submit before the deadline. Okay, I'll see you next time. Bye.